Okay, this is my solution for the problem that we did on Friday of week 7. And what we did this day was we were looking at accident reconstruction. And we looked at the case that the cars collide, stick together, and come to stop at some point on an angle at a 90-degree corner. In other words, it looks like this. We have one car coming in this way, and another car coming in this way, and they have some speed. So this is a car M1 traveling at, V1, and this is a car M2 traveling at V2. And then what the officer sees later is a bunch of broken glass where the collision happened, and both cars off together crumpled up over here. Okay, so what we know really is we know the distances. So we know the distances aren't so handy until we realize that it tells us the direction of the momentum. So what conservation of momentum tells us is what the velocity of the cars were together after the collision. But of course, by the time we get there, the cars are stopped. And that's because friction has exerted an impulse on this system. So what we're going to do is we're going to look at the before and after, meaning just before the collision and just after the collision. However, this final situation, what it tells us is it tells us the angle right here. It tells us this angle. And so what the officer's probably going to measure is this distance, let's call this y, and this distance, let's call that x. And this is going to help us find the angles. So the officer can look up the masses. Let's just say we know the make and models of the cars, and so we can look those up. And so what this problem is asking is find the ratio of the initials. Find the ratio of the initial velocities. So the way we did in class is, let's say there's reliable witnesses that M1 was traveling at the speed limit. So was M2 above the speed limit, at the speed limit, or below the speed limit? Okay. So this is classic conservation of momentum, and so the sum of the momenta beforehand is equal to the sum of the momenta afterwards. Now, what makes this problem a little more complicated is that this is a two-dimensional problem, and so in fact we have momentum in the x and the y direction. So we have to write those as simultaneous equations. So let's choose, yes, I've already made my choice here, let's choose x and y like this. Okay, so the x momentum says that m2 v2, and that's it. There is no other momentum in the x direction, is equal to, so I'll write this out, this is the x direction, is equal to, well, the cars are stuck together, m1 plus m2, and they have some final velocity, I'm calling this v1 plus 2, and but I only want the x component of that velocity, so it's cosine of theta. Okay, in the y direction, I have m1 v1, and that's it. The other car isn't moving at all because this is a 90-degree corner. So if we had those crazy corners like we do in Bellingham, well, then they'd maybe both have x and y components, but it wouldn't be that much more tricky. And afterwards, again, they're stuck together, and they have some velocity, but only we want the y component, sine of theta. Okay, and so, well, let's see. You can solve this equation for the thing you don't know, which, by the way, is their final velocity, and then plug it into the other one. I'll tell you that one sort of quick way to do this is to simply divide one equation by the other. And so when I do that, I get m1 v1 all over m2 v2 equals, and the masses cancel out, the velocities cancel out, and all that I'm left on the other side is sine theta over cosine theta, also known as tangent theta. So in fact, to find their relative velocities, v1 all over v2 is equal to m2 all over m1, which the officers can look up, times tangent of theta. So what the officers actually know about this is it's m2 all over m1 and tangent of theta, so SOHCAHTOA, opposite over adjacent. And that's it.